Okay. So I apologize also for the slightly cryptic title to my talk, which I've already been told off by Stephen Walker for. The zigzag, this is actually very recent work which I've been working on probably for something like 6 months and maybe less than that. It's unfinished and we don't have a paper out on this yet. We have a paper on aspects related to it, and hopefully we should have a sort of more methodological paper out pretty soon. But it's something I'm very excited about now, so I'm very happy to be able to share it with you, and hopefully you'll find it interesting. It's the last talk in the conference. I'm hoping that there'll be very little that's technical in this talk, and so hopefully it'll be easy to understand at least most of it. Okay, so that's what I'm going to talk about. So the zigzag is an example of non-reversible Markov chain Monte Carlo techniques, which are just starting to emerge in the literature. We had a CRISM workshop. CRISM is a research center in Warwick, which I run, which many of you probably have visited. We had a workshop last year, which was quite a large workshop. We had people from all over the world, and it was really focused on non-reversible Markov chains with a particular focus on simulation. And so I think a non-reversible Mcmc is a very interesting direction, and hopefully I'll manage to convince you of that this morning. I'm going to say something about the sort of main schemes for doing non-reversible Mcmc. Also give you something about the motivation about why it might be a good idea. Obviously it's going to be more complicated than the reversible case, and why should we ever want to bother with that extra complexity. I'll introduce the zigzag, which is the algorithm which we'll be talking about for most of the later part of the talk, which is where I'll sort of explore it. Okay. So this is very much work in progress. And hopefully I'll sort of at least give you some indication how it all sort of, the intuition behind everything, because I think it is quite nice intuitively as a kind of process or collection of processes. And I'm going to start off with something which many of you will know about. It's a very simple algorithm called the slice sampler. This is a toy example where we can sort of see what it does. If you haven't seen the slice sampler before, I'll briefly describe it here. You're interested in simulating from this density. I've made it increasing with a density that decreases down to 0. This is the density, it's one-dimensional. Its mode is at 0. And it has trajectories. Essentially what it does is it has an auxiliary variable, which is the height of the density at any location x. And the Markov chain proceeds by doing a Gibbs sampler on the epigraph, which is this area under the Markov, under the density itself. So for instance, it might start here and move down here and then go down there, whatever. The slice sampler is a very interesting process. So this is just the simplest possible version of it. It turns out to have very good, in fact, convergence properties in many interesting situations. But we're not going to be talking about that today, but I just wanted to draw that diagram just to say, well, actually, if we think about this diagram here and think about this notion of the height of the density here being a natural auxiliary variable, there are other ways in which we might want to think about using that diagram. And I'm going to just sort of introduce a basic one, which we'll return to later in the talk. It's a very simple idea. So what I'm going to do here, I'm going to make the maximum value of my density equal to 1. And I'm going to get a uniform random variable, and I'm going to draw this uniform random variable between 0 and 1. I've taken this value here, around half. And then what I'm going to do is I'm going to have a particle here, and I'm going to basically send it along here with constant velocity until it essentially gets to a region where it's about to exceed the density, and then I'm going to send it back again. Okay, so it's going to kind of hit there, and then it's going to come back. Okay, when it gets back to the mode here, we'll have to do something different. So actually what you do is you pick a new uniform random variable, and then you do the same thing again. Now it may be sort of intuitively fairly obvious that this Markov chain will have the right stationary distribution. I mean, essentially, what's the probability that in one of these excursions you include, say, this value here? Well, that probability is essentially just going to be the same as the probability that this uniform random variable will be below that level. which is basically going to give. So it's sort of it's natural to see that the probability of you actually including any one point is going to be proportional to the value of the density at that point. And therefore, this is a non-reversible Markov chain. It's highly non-reversible because actually it has this kind of constant velocity, and it's going in a particular direction, and that direction is something that makes it non-reversible. And actually it has the right invariant distribution. Now clearly this isn't a simulation algorithm, but maybe there's something that we can produce a simulation algorithm on the basis of this. Okay, so just for reference, here's our Hastings Metropolis algorithm. We're going to be talking about finite sets, at least to start off with, finite state spaces. So here we have P is, this should actually say Q to start off with. This is the transition probabilities on S. Pi is the invariant distribution. A is the acceptance probability. Usual Metropolis Hastings acceptance probabilities. The transition kernel, I've got my Q's and my P's a bit muddled up here. This should actually be a P, and that one here should be a Q, so I apologize for that. And these should be P's as well. So the Metropolis Hastings chain is actually reversible. It's a reversible Markov chain. Pi is invariant for P, and everything works very nicely. And we all know about the flexibility in this kind of, and the power behind this kind of procedure. Now, okay, so that's a simple reversible Markov chain and a flexible way of producing one. Of course, reversible Markov chains are good. They're good for various reasons. I mean, they're mathematically very clean. There's very nice properties of a Markov chain, which is reversible. It has, for instance, its transition operator is self-adjoint, which turns out to be a very nice property for lots of mathematical and practical reasons. Spectrum is real. There's also very clean links between a chain and things like the existence of central limit theorems, which we do care about quite a lot for MCMC because we want to do estimation. Okay, so there's very nice theoretical properties. Moreover, the reason why we use reversible mechanisms for MCMC is really to do with the fact that actually doing the accept-reject step is very easy. It's just basically determined by detail balance. The detail balance condition is a local condition. It doesn't need you to do any calculations. It doesn't need you to calculate any kind of integrals or anything of that kind. Okay, so that's nice. So why would we ever bother to look about anything further? Okay. But actually, if you look at the probability literature, it's been well known for quite a long time, certainly back to the sort of early 90s and before that, that when you look at classes of Markov chains with a given invariant distribution, it's very common for non-reversible ones to do better. In fact, it's very common for non-reversible ones to do considerably better. And in sort of toy MCMC situations, you can even you can actually quantify this in some simple situations. So for instance, this last paper here was an attempt to basically show that this might be useful for MCMC but without any sort of practical relevance, really. Okay, so of course, I mean, there are algorithms which try to actually adopt the kind of character of non-reversibility. Hamiltonian MCMC is the most successful one, and it's a very, very successful technique in all kinds of areas. Many of you probably have experience of it. This tries to construct chains with a sort of non-reversible character, but actually, of course, it's not non-reversible at the end of the day because it uses an accept-reject step. And accept-reject steps always essentially then produce something which is like a detail balance condition, which is gives you the stationarity. So that's one way of trying to do things, and that's obviously very successful, but maybe we can actually go for things which really are non-reversible. Okay, so that's the Metropolis Hastings that we saw before with all the Q's and the P's in the wrong direction, but that should be okay. This is non-reversible Metropolis Hastings. Oh, I should have said at the beginning, this is joint work with Joris Perkins, who's a research fellow at Warwick, and also with Paul Fernhead. So he has a very nice way of producing non-reversible Metropolis Hastings on this finite state space. in the following simple way. You look at your acceptance probability here, and essentially you perturb it. And you perturb it in a way which is which is basically producing the non-reversibility. So you have this function gamma xy, it's a matrix in this case, which is we call it a vorticity matrix. It's producing some kind of spiraling round in some appropriate sense, in some general sense, in the Markov chain. So this is essentially what you do. You have this acceptance probability, and everything else proceeds as it does before. And you can show quite easily that actually you get reversibility. Sorry, you don't get reversibility, but actually you do get the nice properties of invariance. Okay, so that's all very nice. Okay. So this is an example of a very simple Metropolis Hastings algorithm, which is actually reversible, and it's basically on the discrete circle, and it's basically you've got three modes here. Now this is the standard Metropolis Hastings algorithm, which basically gets stuck, and it's actually finished there. It actually gets stuck in this mode, and it really struggles in the way that multimodal distributions often do struggle with all sorts of algorithms. Okay, so with this vorticity matrix, what happens is that you essentially, in this case, we have a sort of anti-clockwise momentum, and that's a sort of permanent momentum, and that sort of pushes us through all of these different modes. So you can sort of see that you're getting some real help from the non-reversibility here. Okay. In some sense, this is a very fair comparison because you've got, in some sense, you're trying exactly the same moves. You're proposing exactly the same moves in both cases, in all these cases. And of course, in less toy examples, you can make the advantage much more considerable, especially when the multimodality gets worse and worse. Okay, so maybe there is some motivation for doing this after all. But what's the bad news? The bad news is that, unfortunately, it's very difficult to do this in general. So, for instance, remember that we had an acceptance probability here, and here's our little vorticity matrix here, gamma xy. Of course, we want that acceptance probability to be non-negative, and that's something which is a constraint. And you can imagine that in a complicated state space, that may be very, very difficult to maintain. Okay. Gamma xy has to equal to minus gamma yx. It's not true that all these things are positive. Some of them necessarily have to be negative. And you can actually show some negative results. So for instance, if you have a three-state example, you can show for a three-state example, you can never actually, you can essentially never construct by this mechanism a sensible, non-reversible Markov chain which has the right invariant distribution. So there's big limitations on this, and the limitations are really caused by the fact that we're working in the same state space and not expanding the state space in some sense. So if we have a state space like this, maybe there's a more general way in which we kind of introduce this notion of kind of momentum, and this is essentially what we can sort of try and do. And so the procedure is called lifting. And then so what you do here is you sort of artificially create some kind of cycles. Now let me explain what's happening. I start off with my 4 states for my Markov chain, or my state space of interest. I'm now going to produce duplicates of these states, and I'm essentially now going to have these duplicates in such a way that essentially I'm going to be doing something slightly different in the top 4 from the bottom 4. But how can we do that in such a way to ensure that we actually have the correct invariant distribution? Okay. Well, what we do is we introduce this auxiliary variable, which in our case is going to be a plus or minus 1, and that's going to indicate a kind of velocity in some sense. Now, t plus and t minus are going to be essentially what you do when you're in those different states, when you're in plus 1 or minus 1. So you do the t plus transitions when you're in plus 1, and you do the t minus ones when you're in minus 1. They are sub-Markov. That means that their probabilities don't sum to 1. So they don't fully specify what you might do if you're in that particular state. And then essentially, this t plus and minus have to satisfy what we call skew detail balance. Now, skew detail balance basically just says that I've got pi x t plus xy is equal to pi y t minus yx. Okay, so I'm not requiring for the same transition t. I'm not essentially saying that I've got the same t plus and t minus here. If I did, that would be reversibility. So this is a more general condition. But then we have to decide how we move between the plus or minus ones. And essentially, we do that just by mopping up all available probabilities. So essentially, you've got movement here in the positive direction, so that's sort of pushing you to the right, and you're sort of pushing to the left, although you could be doing something slightly more general things, really. And then basically with other probabilities to kind of correct for the fact that you have sub-stochasticity here, you basically jump between the various states. Okay, that's a general construction, but how can you do that for Metropolis Hastings? So let's try and put this all in the Metropolis Hastings context. Okay, so first of all, we need to decide something about this notion of vorticity, this notion of where we're going to try and push ourselves to go. So we introduce some quantity of interest, eta, which is one-dimensional. Now, in the cases that we've looked at, the first case that we looked at was in statistical physics, where we were basically, eta was counting something like the proportion of spins which were in a particular direction. Okay, so when you're almost all up spins, then eta was high, etc. So that's a natural thing to do in that context. In MCMC, you may be actually, in sort of more statistical examples, you may be more interested in having eta to somehow talk about either sort of areas of different modes or sort of different levels of complexity or various things of that type. There's endless options. Okay, so you basically, so now you'd introduce, now what you can do is you can say, well, let my T plus matrix just essentially be all the transitions which increase eta. And I'm going to throw away all the ones which decrease eta. And I'll do the opposite with the minus one. So I'm only ever going to move my up according to eta when I'm in the plus state, and only down when I'm in this state. These don't have to be zero. That doesn't have to be zero, that doesn't have to be zero. But this is in some sense the most extreme thing you can do. Skew detail balance is obviously satisfied. And in practice, so this produces what we call lifted Metropolis Hastings algorithm. So we propose, according to this Q, if a move is allowed, in other words, if we're doing the right thing in terms of eta, in other words, increasing eta if we're in the plus state and decreasing if we're in the minus state, then we accept it with the Metropolis Hastings accept probability. And if a move is not allowed, then we basically possibly switch, and we have to switch with the correct probability. And by switching, I mean I'm switching +1 to -1 or vice versa. Okay, does this solve the problem? Well, you notice that I've been talking about everything in discrete state spaces so far. Well, here's the problem, is these switching probabilities have a horrible form. Okay, in a complicated state space, this is going to be a big sum or an integral. So this isn't going to be something that we can do. And we absolutely need to know what these things are in order to actually implement the algorithm without some kind of bias. Okay. So that looks like it's giving us another block. So both those mechanisms, one introducing the vorticity matrix, and this method here, which essentially involves us having to duplicate having the pluses and minuses, both seem to give things which are going to be intractable for hard problems. So you can't generally apply it, at least in its pure form. What happens, and I'm not going to talk about the mathematics of this, is that you can actually do some interesting things here, because what you can do is you can actually mathematically take the limit of such an algorithm in a continuous state space. You can write it down as a theoretical algorithm, which you can't actually implement. But then you can actually speed up the process and make very, very small jumps and converge to some kind of continuous time limit. I'm not going to describe that mechanism because I'm actually going to tell you what the limit is and sort of miss out that kind of detail. So this is the first paper that we did, which was actually on this statistical physics model in which we sort of implemented this. And we actually proved this sort of limit result in that context. But the thing that was interesting about that work was we discovered that even though we were interested in that limit from a theoretical probabilistic point of view in that paper, it turns out that you can simulate that limit, and simulating that limit process is much easier than simulating this particular process. And that's something we didn't realize until we've done that. Okay, so, and in fact, this continuous time limit object extends very easily to a sort of very simple process that we can describe. Okay, and the sort of processes that actually are going to be coming up now are sometimes called piecewise deterministic Markov processes. They've been around a long time. This is Mark Davis, the probabilist who published a paper in RSSB in 1984, in the good old days when RSSB would actually publish probability papers. But it's a very nice paper, but it's completely theoretical probability paper, which is really looking at the mathematical properties of these things. Now, what are they? A PDMP is essentially a Markov process in continuous time, which is piecewise deterministic. So it essentially has some deterministic trajectory, which is typically given by an ODE, and then at some particular time, which is determined by the sort of dynamics of the process, those dynamics change completely. So the randomness only comes in those kind of change points. Okay, so that's what these processes look like. And we're going to be looking at this as a continuous time MCMC algorithm. And continuous time MCMC has been something that I think a lot of people have sort of played around with. By that, what I mean is an algorithm which, in principle, runs mathematically in continuous time, rather than a discrete time algorithm. And of course, discrete time algorithms are sort of very natural for what you do on a computer, but it may turn out actually that continuous time things are actually easier to implement, as we'll sort of see. So this is just I know of lots of examples of this. Apologies if I missed anybody's name off here, but there are lots of people who try to do these things. But in many ways, the existing continuous time MCMC methods can be just thought of, in some sense, as natural continuous time analogs of what you have in discrete time. I think the PDMPs are really completely different in character, and I think that's one reason why they're exciting. And certainly the convergence properties are very different. Okay, so they're often very easy to simulate, as you'll see. Okay. Okay, now we started off by talking about a very simple example. And this toy example, and I'm going to explain how this is related to what I've just been talking about. Remember, what we said was we drew this uniform random variable, and then we essentially went on a journey along this trajectory with constant velocity. It's important that it's constant velocity. And then you just essentially come back. Okay, so another way of thinking about that is say, well, let's forget about this uniform random variable. Let's instead essentially have some hazard rate. I'll sort of start off on this journey. In fact, I'll go on this axis here. I won't have an auxiliary variable. I'll just know I'm actually moving to the right. And then with some hazard rate, the hazard rate turns out to be the maximum of 0 and minus the derivative of log pi. Okay, so at that time, I'll essentially swap direction. Very easy to check that that's completely equivalent. Okay, the probability that this thing gets as far as here and no further is exactly equal to the probability this uniform random variable is that value. It's a very simple calculation. Okay, but this suggests that maybe this is the sort of natural analog of the sort of lifting thing in continuous time. So what you've actually got here is you've got some hazard rate of changing direction. Okay, so the one-dimensional zigzag process. Just for comparison, if you look at Langevin diffusions, which are often used in simulation these days, it has a generator, people interested in that sort of thing, which actually is a second-order differential operator. These things are complicated mathematically in comparison to first-order operators, and in terms of simulation, there's certainly a lot more that you have to sort of worry about. And in particular, of course, diffusions are typically hard to simulate exactly. In contrast, if I look at piecewise deterministic Markov process, or the zigzag in particular, it has a generator that's much simpler. It's just a first-order differential operator. And essentially what all you need to specify, and you have to specify it in a particular way, is that you've essentially got a velocity, which is a in this case. J is basically the current direction. And then lambda yj is the rate at which I'm jumping between the plus state and the minus state. And as in this sort of, let me just go back to the previous slide, one might expect that this kind of simulation here would have really quite nice antithetic properties, right? I'm equally going to all of these kind of locations, and I'm basic, so it seems that it's sort of averaging out in a sort of very, very natural way. And this is a kind of, this is a trajectory that you might get from a simple example. So you very often get situations where you have sort of a very antithetic type behavior, where it really is sort of looping through the state space and kind of averaging over sort of all the places it wants to do. So in terms of empirical properties of asymptotic variances and things like that, the algorithm performs extremely well. So what about these switching rates? Because the switching rates were the things that were the problem for the lifting mechanism in the context of the basic algorithm we looked at originally in discrete time. Okay, so all we basically need here is for these lambdas, these jump rates, to satisfy the following: that the lambda from jumping from j to minus j, minus the rate of jumping back, has to equal aj, and this phi is essentially the log of the density. So this is log pi prime, if you like. Okay, so the difference between those two things is equal to log pi prime. So actually, therefore, we can specify this algorithm in the following way. We can just say that lambda yj is equal to some generic jumping rate, which is a jumping rate between +1 and -1, which doesn't really mind whether I'm in 1 or -1, and then this kind of maximum thing. Okay. And so you can actually show that in some sense, I mean, it's trivial, that in some sense the one which switches less is the one which sets gamma to be 0. And that's the one which essentially is the one I was showing the toy example for. That's the one that switches less, and in some sense has the most non-reversible character, and the momentum has the highest possible persistence in that case. So it's of particular interest to look at cases where gamma is equal to 0, or at least relatively small. Okay. Okay, so it turns out that there's lots of people interested in these kind of things. Not many of them to do with simulation. Here's just some body of literature related to these PD MPs. The exception is this very nice work by Arnaud Doucet and Sebastian Vollmer and a colleague, which came out last year, which is the Bouncy particle sampler, which actually has very similar properties of the kind of thing I'm talking about. There's some important differences, but this is very sort of interesting related work. Okay, how are we doing for time? How are we doing for time? Yeah. Okay, thanks. Yeah. Okay, thanks. I'll right, thank you. All right, so I promised Flavio I wouldn't go over. So mathematical properties, well, I'm going to skip over this largely. It's non-reversible, as we've been sort of focusing on. It turns out it's not a strong Feller process, it's a weak Feller process, and that has some sort of implications in terms of the mathematical ways in which you analyze these things. And it has some, the resolvent is quite a complicated object. And this, again, I'm not going to talk about this too much, and this is a theorem again which I'm not going to talk about, but it's to say that since these processes are so simple, it turns out that actually proving theory for them is actually much easier than, for instance, proving similar kind of results for standard Metropolis Hastings algorithms. So exponential ergodicity, for instance, under certain conditions. Okay, and that's even a sketch of the proof if anybody ever wants to. Okay, how on earth do you simulate this thing? Because it has a hazard rate, but this hazard rate will be a locally bounded function unless you have a pretty badly behaved target distribution. So you could just use standard techniques involving thinned Poisson processes. So you have a Poisson process which basically tells you, I might be changing direction here, and when you do change direction, it happens because you've tossed a coin which had a certain probability. So by doing that, you can really minimize the number of times you actually need to compute the gradient of log pi, or this phi prime object. So this makes the algorithm pretty inexpensive to implement, and you only need to calculate, as I said, grad log pi occasionally. I'm not going to go into a lot of the details because I want to just sort of impress on you the sort of simplicity of the method today, largely. Again, just another very simple one-dimensional example. This is in comparison to, this is a Cauchy distribution in comparison to a random walk Metropolis algorithm. The purple is our zigzag process. The black one is the Cauchy process. You might look at either of them as being better there, but if you look at it over a longer time period, then actually it turns out the zigzag is massively better. The excursions into the tails are much, much more stable, as you'd expect, because it just kind of goes into the tails and comes back. And in fact, it's well known that random walk Metropolis can't really sample from even a one-dimensional Cauchy distribution, and you can sort of see it here. It just completely misses the tails. And by the way, this isn't an optimized zigzag. You could actually, if you've got heavy tails like this, you can actually improve on the zigzag quite considerably by speeding up as you go out into the tails. And that's a very easy fix, but I won't talk about that. Okay, so the multidimensional zigzag. So how on earth do we do this in multi-dimensions? Well, essentially, there are various ways of trying to do this. This is the way we've come across as the simplest and the one which sort of generalizes in the most natural and computationally easy to do way. Your velocity now is essentially a sequence of ones and minus ones. So you have a velocity for each component. Okay, and essentially what you do is you have one of these, and any one of these velocities can actually flip at any particular time. I've got, again, a little toy example just to show. This is just on a sort of, well, a little bit like a non-symmetric banana distribution. This is what the zigzag looks like. In 2 dimensions, you can see that its directions are always going to move like that. Now, at those junction points where it sort of moves at 90 degrees, that's the times at which you need to do a calculation of the gradient of log pi. This is a continuous time object. In principle, you might take all of that sample path, all the continuous sample path. In practice, you probably can't do that. For some functionals, you may well be able to do something nice, but you end up with something that looks like that. And it very naturally sort of moves around, and it prefers certain types of directions in different types of the state space where you essentially have different shapes of curvature, etc. Okay, right, so there are some other exciting things that you can do with this, and this is subsampling is one which Steve was talking about this morning. I'm very much interested in subsampling methods which don't give anything away. In other words, subsampling methods which are exact in the sense that there's no approximation in terms of the invariant distribution. And so this is the sort of, this is why subsampling is difficult when you have intractable likelihoods, in the sense that the likelihood contains a product of so many terms that this is actually not feasible to calculate at every iteration of your algorithm. Okay, so you can think of n as big data if you like. Steve would probably tell me off, but it's, I mean, it basically, this could be, there are many contexts in which you might want to do this. So what might you do? So of course, what you might, so if you have, you might want to do some method which still simulate, essentially only needs to compute a certain number of these terms. And what you want to do is you want to have some computing mechanism for pi which is little o of this capital N, if at all possible. So you want to be as lazy as possible as well. You want to use as few of these terms as possible. And of course, one thing you might do is you might try something like the pseudo-marginal MCMC method for getting unbiased estimates of this. But unbiased estimators of a product are horrendously difficult to do in a computationally good way, which basically doesn't involve you having a massively high variance. So this, it turns out to just be completely impractical. What you'd really like to do is you'd like to turn this exponential into this product into a sum. As soon as you've got sums are very easy to estimate, unbiasedly, without any problem. Continuous time is a natural situation in which products get turned into sums because you're just looking at sort of incremental changes. And that's why, and of course, in the kind of algorithms that we've been working with, we've been talking about today, everything's governed by the log of the target distribution, and because it's governed by the log of the target distribution, that's, in this context, going to be given by a sum. Okay, so in our case, we have a situation that minus log of pi is just given by this nice sum. And you can certainly get unbiased estimators of this guy very easily. But there's a problem, because in the context of the zigzag algorithm, we're not just working with this, we're actually working with something which is the maximum of 0 and the direction j times this sum. Okay, so if I was to basically put in an unbiased estimator here, I would have something that is not unbiased for this maximum object. Okay, but the remarkable thing is that despite doing that, this algorithm still works and still gives you stationarity. Because what happens is that the expected value of the expression that you get in here when you actually do subsampling is exactly the same whether I take j to be +1 or -1. Sorry, the bias is exactly the same. So the bias just turns out to be some extra little switching rate, which is changing my +1s to -1s. And in that way, it preserves the stationarity. Okay? It's a calculation that we did about 23 times because we didn't quite believe it was true when we did it the first 22. Okay? So it works. Okay? So it turns out that, you know, when you have a product or a sum like that, so if you want to do something like an order 1 update in the state space, if you don't use subsampling, then basically the computing cost is something like order capital N. Well, it's going to be because you compute all the terms. If you use subsampling, it turns out you gain a factor of N. Make it, I've written this in the right way here. Okay, so I'm not sure I understand exactly what I've written here, but let me just say what it really is. So if you use subsampling, it turns out you gain a factor of n to the half. Okay, and therefore that reduces the complexity to order n to the half. But it turns out that there's a really nice control variate trick. Again, very simple techniques, but it's a control variate trick in this context that you can actually also gain another order n to the -1/2. So it turns out that you can actually do a sort of an order 1 cost update in this context. In other words, you can have algorithms which in principle don't involve you having to sample all those. And in fact, when you go back to, well, you might, sorry, where am I? When you look at this expression here, this expression here, you might ask the question, well, okay, I get an unbiased estimate at whatever, but how many of those terms do I need to take? It turns out very few. It turns out that you don't want to take it to be 1, but you can really take it to be a small number, often less than 10. So this is something that you can do very, very nicely. Okay. And this is just illustrating. This is on a logistic growth model where we had two parameters. So it's just a 2-parameter model where n is a sort of the size of a data set. At the top, we've got 100. I don't think you probably can't see this very well at all. But essentially, what we've tried to do here is we tried to draw one of these kind of red circles every unit of computing resource that you're using here. So for this is on the left-hand side here, it's essentially the algorithm without subsampling. You can see that basically there's loads of these red ones here. This is the one using just subsampling, and it's sort of, the red ones are sort of less frequent, so this is actually much quicker. It's 100 times faster, so 10 times faster. And this is the one we're using subsampling and control variates, which is in principle and in practice 100 times faster. And when your data set is of size 10,000, then you gain a factor of 100,000 when you start, and even this is robust to starting way out in the tails. You see that there's lots and lots of red circles here, but actually there aren't any at all on this transient path here, because it zooms straight into the station distribution. So we've done models like this. It turns out you can implement, we haven't really done anything huge. We've done sort of 100-dimensional logistic regression type examples. Again, they're quite robust, well, they're very robust to the size of a data set, but we've got an awful lot more empirical work to do to investigate these things. Okay, just to finish off. So we think it's fun. It's a flexible and easy to use method for simulating from distributions in a very general sense. It works because it's in continuous time, and you can implement it. And that, to me, is very exciting because it's very different, I think, from sort of previous attempts to do continuous time Mcmc. The subsampling and control variate tweaks are very important for efficiency, and they can be used in other contexts as well, other intractable likelihood type contexts. So we're sort of very excited about possibilities there. Again, we're still exploring them. We've got a lot to do. The theory is very interesting. It turns out that it's actually hard to even prove things like irreducibility for the pure zigzag in some cases. And it's interesting. I mean, you can get around, from a practical point of view, that's nothing to worry about because you can sort of get around it. But actually, the theory is interesting, and it's not clear to me exactly, how generally the irreducibility will hold for the pure zigzag. I mean, it's an easy thing to implement. It's using gradient information in the same way that Hamiltonian MCMC is. But actually, it's going to be much simpler to implement. So can this be a competitor? It might not be. We don't really know. Just a general comment. So we've actually been working a lot in 3 separate projects, in fact, which coincidentally all turned out to involve PDMPs, these piecewise deterministic Markov processes. They're very natural, and they come up in sort of interesting kind of cases. Even surprisingly, some which are based on diffusion algorithms, where in principle you're simulating a whole diffusion. But it turns out there's a sort of sufficient statistic which is running, which can be interpreted as a PDMP, and then you can analyze all the theory in the context of the PDMP. So these are very important to the things that are developing. And I wanted to highlight another exciting project which I've been doing called the scale algorithm, which is joint with Murray Pollock and Adam Johansson, both at Warwick, and myself and Paul Fernhead, which actually is similar. It's an example of this PDMP thing, but it actually works with diffusions, and it turns out that the invariant distribution that well, it's not an invariant distribution we use here for simulation. It's something called a quasi-stationary distribution. And quasi-stationary distributions are defined to be limits of Markov processes conditioned on various things. And so it turns out to be that I haven't seen quasi-stationarity used in the context of simulation at all. And so I think it's very interesting to sort of to bring that in. And it turns out in the context of a scale project, you have to use quasi-stationarity, and you can't use ordinary stationarity, which is sort of intriguing and sort of that's very interesting. This also has applications to sort of the big data type problems, intractable likelihood type problems, in the same way that the zigzag process does. Okay, I think I've come to the end, so thank you very much for your attention.
So will the proportion of switches, like the switches zigzag, will that give you like a convergence diagnostics or diagnostic for the target distribution, like it's a tough problem or easy problem?
So the invariant distribution of the whole process is essentially pi producted with sort of independent plus minus ones, right? So if you just look at your switch things, I think you're going to miss things because you could easily have the switching converging much more rapidly. Okay.
No, I think the switch rate, like what proportion of times it is switching, like sort of Metropolis Hastings acceptance rate.
Okay, so yeah, I see what you mean. So yeah, but I think it's possible that the switch rate could be fairly heterogeneous, homogeneous, and you know there could be areas of a space which are very different, which have the same switching rate. So yeah, well, I'm not saying it's not. I mean, you know, anything is useful as a
I think something could be explored there.
But I would have said it wasn't the sort of obvious first one to use. Yeah.
And also, if your target distribution, remember the target distribution you draw, if that has a bimodal that has a mode somewhere in the middle, then it may switch more or less. So that may take quite a lot.
Yeah. So when you're in a mode like that, yes, you will switch more. Yeah. And if you've got these kind of long tentacles or ridges or whatever, then your zigzag will sort of shoot out along those ridges. I mean, it might have to change direction a little bit, but it will sort of go out along those ridges and it'll probably switch less. So yeah, you'll definitely get that kind of thing. Yeah.
Any more questions? I have a quick one. Do you have a magic number like 0.234 for the acceptance rate of the lifted Metropolis? Can you work it out if you don't have it yet? Does it depend a lot on the gamma function?
It's a good question. So in some sense, there are degrees of freedom in the algorithm. So you can have this extra switching, which basically says wherever you are, you can just switch anyway. To make the thing as non-reversible as possible, you want to set that to be 0. So in some sense, the extreme is at the bottom end. But it's at that 0 case, that's the only case where we cannot prove irreducibility. So actually, sometimes you might want to take it to be slightly bigger than 0 anyway. The other thing to say in terms of optimization, though, there are still questions. So there is a velocity in there, which I didn't talk about much. When that velocity is constant, it turns out that there's no gain, there's no advantage whatsoever to changing it, because it's essentially, everything scales in time. You just do a time change and you're back to where you were. And in terms of computation, it's exactly the same as well. However, if you've got something like a heavy tail distribution, then you may well want to have one of those things where you sort of start going out along the tail, and then you realize you're not changing direction, so you want to speed up. Okay? As long as you can solve the ODE, and you can construct that ODE however you want, okay? It has nothing to do with pi. You need to be able to know where you are, okay? As long as you can solve that ODE, you can actually sort of say, right, let's really shoot out into the tails, because I really suspect is a very heavy tail. And so there's lots of interesting questions there, which no doubt have sort of implications for optimization. Yeah.
Thanks very much. So let's thank Gareth again.